Alright folks, this is the last video for this section. It's on relative motion, and the idea behind this is now the observer might be moving, or at least multiple things are moving here. This scenario is like a classic situation in physics textbooks where we have this cart that's really long, and two people are running toward one another on that cart. The cart is moving also. So the cart's moving at 10 meters per second right. Person A moves at 4 meters per second to the right on the platform. Person B moves at 4 meters per second to the left on the platform, and there's a third person, C, who's just standing off to the side observing everything. We're going to decide that to the right is positive, at least for A and C, and we're going to look at their perspectives. So according to person C, who's not moving, we're going to think about the velocity of person A. Now, they're on a platform that's moving 10 meters per second, and they're also running at 4 meters per second. And so these two velocity vectors are pointed in the same direction, and so they add together. So the person's velocity plus the platform's velocity gives us a velocity of 14 meters per second to the right. So relative to the ground, the person A is moving 14 meters per second to the right because they're on that moving platform and they're moving on top of the platform. The same thing is true for person B, except because they're moving to the left, they have a velocity of -4, and the platform still has a velocity of +10. This means that person B is moving at a velocity of +6 meters per second. So they're still moving to the right. If like person C were watching this event happen, even though person B is running to the left, the platform is much faster, and so their body is actually going to be moving to the right, according to person C. So this is an inertial reference frame that's at rest, and that's kind of like a normal thing that can happen, that two velocity vectors add together to make the final velocity. If we move to person A being the observer, then things get like a little more odd. We can't make this simple math work anymore. So we have to like consider what's happening together. So according to person A, they're going to look at the velocity of person B. Now, they are, actually we can make this work really easy if we use these answers. Person A, relative to the ground, is moving at 14 meters per second to the right. Person B is moving to the right at 6 meters per second. And because person A is moving, their like own velocity runs like counter to person B. So we end up finding the difference between these two. So we have 14 meters per second is how fast that person A is moving, and then person B is moving 6 meters per second. They're moving in the same direction, and so the velocity of person B, according to person A, is only +8 meters per second. I want to think about that in a different way. Every second, person A travels 4 meters to the right on this platform. Every second, person B also travels 4 meters, but to the left. So what's actually happening is person B is getting 8 meters closer to person A every second. It doesn't actually matter that they're both moving. If A is the observer, then their reference frame is like moving with them. And so person B appears to be moving at 8 meters per second at them. And I got this totally wrong. I should have switched them. So I'm going to leave this mistake in. Person B is moving at +6 meters per second. Person A is moving at 14 meters per second. If we take the observer's velocity away, we get -8 meters per second. So they appear to be moving 8 meters per second to the left. Okay. Person C is a slightly simpler example, because person C is not moving. So relative to the ground, person C has a velocity of 0. However, person A is moving 14 meters per second to the right relative to the ground, which means that person C appears to be moving 14 meters left every second. And so if we, again, take person A's velocity out of this, then person C appears to be moving at 14 meters per second to the left. Now, you've all been in vehicles before, and so if you look at a traffic light as you're driving past it, you're going forward, and you can kind of trick yourself into believing that the traffic light is moving toward you. So this is what I'm trying to capture here with relative velocity. You will not have to do this in AP Physics 1 very much, but you might have to think about it a little bit. I think as complicated as I've seen in the AP exam is this according to person C, where you have a person who's observing that's not moving, and then you have an object that's moving within another object, a train car or a platform or a boat on the water or something like that, where you would add the velocities where they're moving together or subtract them if they're moving in opposite directions. I wanted to show you another way to apply relative motion. You did this problem. A bunch of you asked me about it because it's a harder problem where a bear is chasing a tourist toward a car. The bear and the tourist have different velocities. And when you think about what's actually happening, in 1 second the tourist moves 4 meters, and in 1 second the bear moves 6 meters. That means every second the bear moves 2 meters closer to the tourist. So if I take the tourist's perspective, the bear has a relative velocity of 2 meters per second. In other words, the bear is gaining 2 meters on the tourist every second. I can use this to solve the problem in a very different way. I can use this simple motion equation, and what I can imagine is the problem is over once the bear has closed this 26 meter gap. So 26 meters equals 2 meters per second times the time it takes the bear to catch up to the tourist. That means that the time is going to be 26 over 2, which is 13 seconds. This is interesting because it takes this distance d out of this part of the problem and just says, well, the tourist is moving, but the bear is moving 2 meters per second faster. So if all I need to do is figure out how much time it takes for the bear to catch up these 26 meters based on its relative velocity. Now I'm done with relative velocity. The actual problem was to find that distance d. And so if I take the tourist's data, I can say that they're going to move distance d at their own speed of 4 meters per second over 13 seconds, because the tourist's actual velocity relative to the ground is 4. And then the time it takes the bear to catch up to the tourist is 13, and 4 times 13 is 52 meters. So I just wanted to present you with another way to solve this problem. These last two videos are really small parts of this unit in this course, but if you if it clicks with you, it can be really helpful to play with this as you're doing more physics problems throughout the year to see if it's something you can apply. And that's it.